Howdy, howdy. Okay, so today you got a sub. I'm going to go over specifically the Waves presentation, but just to make sure, if you want to get credit for today's work, you should be going through the subfolder in Schoology and clicking those links, and that way it will let me know that you've clicked on those links, and hopefully you've done the items that you're supposed to do. So, anyways, there's all this stuff there. There's videos for the warm up. There's a video audio for the Project Hail Mary book, and of course, there's a YouTube link for Tesla Part 3B. Actually, the last questions on the page, and then of course we're doing Waves presentation right now. So Waves presentation actually starts on this page, and there's a lot of stuff to cover with sound. Sound is Waves Part 2, so a lot of stuff here. Let's just go ahead and get to it. Interference. So interference of waves is where two waves overlap, and when they overlap, they can actually make them the combined effect will be either larger or even smaller. If you're ever been jumping on a trampoline, you would know that if you time it right, you can make somebody go higher. Sometimes people call it a double bounce, and then you can also actually steal their bounce if you time it right. And it's like if you overlap two waves at once, it becomes twice as strong. But if you do opposites, they cancel each other. So we would call that positive and negative reinforcement. So if you look at these things, we have these two waves are in phase. They are in step. They would be laid right over each other in phase, and so they would actually combine and make themselves stronger. This is like when two people are singing together; it gets louder than just one person singing. And then these two waves in the bottom are cancellation, where they are exactly out of phase. That's how your headphones that are like your AirPod headphones that are noise cancellation. They actually do this purposely. They actually have a microphone to sense the outside sound, and then they will play the exact opposite, opposite out of step sound, and they actually cause cancellation. They can actually fully cancel the sound, and so you get no sound coming through. Um, Anyways, those two things are what are called interference, and positive interference is when they increase. So, for instance, this top one would be like, if I had, one was my amplitude and one was my amplitude of the two individuals, then you would have two as an amplitude as your result. And then the other one, if I had a positive one and a negative one, then obviously you add those together and you get zero. So then the next thing we have is standing waves, and the standing waves are actually pretty nice to demo in front of the class, but I wasn't able to demo that because obviously I'm not there. And anyway, so you can do this with a real slinky, and what you basically do is if you do it the right frequency, they'll just go up and down. That's pretty obvious. But if you do it another frequency, you can get them to actually do that, and you can get them to actually do that, and it will just be a standing wave. The wave will just be going back and forth and back and forth, and it just makes a pattern. And obviously, you can do it quite a bit. Um, I'm going to show you over here on the right because when you have it done with a string, this is a real string. The other one's just a simulation, but this is a real string. It's the exact same idea. There's one loop there, and if you just change the frequency of this, it will make a different pattern and make more patterns, and you can basically make that's a real lady talking because I can't remember if this is picking up the sound of the. I know it's picking the sound of my mic, but I'm not sure if it's picking the sound of the YouTube video. But anyway, so you just adjust it differently, and if you make it higher frequency, you can catch more waves. Now that's pretty cool, right? Whatever. But I think the coolest one of them all is actually in a pool. So this is the Navy. It's called a Seiche, Seiche tank. I guess maybe that means wave in German or something like that. I don't know. But these are standing waves, and they're made basically by by water, and if the water goes at the right pace, right? You can do the same thing as you did with the slinky or the string with the actual water, which is actually kind of crazy. So those are called standing waves. And the most important thing about standing waves really is, let me just see a couple, images. It's getting smaller there. It can get pretty crazy. They're changing the frequency of vibration. That's about it, I guess. Anyways, so, musical instruments are a lot like that actually. When you have it tuned correctly, when you have it tuned correctly, that guitar string will be tuned to the right tightness that it actually sets up a standing wave that you can't see. And that standing wave is gonna have a resonance, and that's where we get the A, B, C, D, E, F, G, right? A, B, C, D, E, F, G, the 7 waves on our scale are, those specific standing waves. So, moving through this quite quickly, the, sound and air, and so this top one basically says that we have the bell, and the bell is ringing, and it makes these vibrations, and these vibrations are gonna emanate out as longitudinal waves. They're called compressions and rarefactions. So, you can see kind of in the bottom here, there's places where the molecules are highly compressed, and then right next to it, there's places where the molecules are spread apart, and it travels with these compressions through the air, and it creates these high and low pressure, and that high and low pressure actually makes your eardrum move, and your eardrum will move in unison with the vibration of the source. So if it's a bell ringing, or if it's a tuning fork playing a tone, right? It'll Your ears actually move in the same pattern as the object that's playing it. So just a visual really of the tuning fork. And so you take this tuning fork and you strike it, and they're vibrating, and you can kind of see that in the video right there. They're vibrating. But then there's a visual that they're going to do here, and it basically says that the waves are going out like that, right? And so as the waves go out, they're just pushed, and you get this compressions and rarefactions and compressions and rarefactions as it goes out. Another way to kind of visualize it is the molecules themselves are being pushed, and those compressed parts of the wave are moving um, through the air. And so, as you can see, the compressed air is moving like this on this view. Another one, and I really should do this when you get back, but when you open a door in one side of the house, sometimes a window or another door in another part of the house will open automatically. And that's because the air actually is moving, and these compression waves are moving through the air, and it's changing the pressure on the sides of the door or the sides of the curtain or whatever that we're talking about. So this one is really talking about how sound waves travel through the air, and they travel through the air as compressions and rarefactions, and this compressed air is kind of traveling from the source, which is whatever is the vibrating source. Right now, the vibrating source is my vocal cords, to your ear, and that's the place where it ends up. Okay, media that transmits sound and the speed of sound. So this one really is showing you that you need air in order to actually, have this work. So, this kid comes in, he asks his cousin or his uncle or whatever, "How does sound work?" And so he's gonna set up a demo, and the demo says, "Oh, I got vocal cords," right? So, kind of a silly little video, but what they have is he's got a bell jar, and this bell jar actually is gonna have a pump on it, and that pump actually removes the oxygen, not the oxygen, but moves the air, just removes the air, creates a vacuum on the inside, and so what ends up happening is the bell will ring, and then when the oxygen or the air is removed from the jar, the bell seemingly stops ringing, but it actually never stops ringing, it's just that the air is removed from the jar. So I'm not sure, I can't remember if you can hear the computer sound, but so right now, if you could hear that, that bell is still ringing. when he lets the air back inside with his hand, you can hear it again. So hopefully you can hear that, but if you can't hear that, maybe you'll get the idea. I'll have to explain that to you later, or you can just play it for yourself in the video that's online, right? If you follow the presentation yourself. So really, what we're looking at in that one is this picture right here, and you can hear it ringing. These are batteries, and so he's connecting the batteries. So as soon as he connects the batteries, the line for the battery, the wire from the battery goes into the jar like that, and it's got a stopper. And this is a suction tube. It sucks the air out, making a vacuum on the inside. And so you can hear him ringing when he connects the battery. And then as the air gets sucked out, you can't hear them anymore, but they are still ringing. That he didn't stop the battery from going, so they are still ringing. And the way you notice that is he's gonna thing at the top. It's called the stopcock, and you just basically twist it, and it allows the air to go back in. And as soon as the air goes back in, you can hear it ringing again. So the point is, could you hear somebody talking to you on the moon? And the answer is no, because there's no medium for the sound to travel through. Sound usually travels through air. I mean, if you're a dolphin, sound travels through water, but as a human, sound usually travels through air. And since there's no air on the moon, you couldn't hear anybody. So continuing off of that, the speed of sound in air is about 340 meters per second, right? And it tells you feet per second as well. Water actually is much better, and that's why. So, for instance, many animals in the water do use those shock vibrations from the water to actually know what's out there. A shark will basically be able to know if a fish is in distress by the vibrations the fish is putting off, and the shark can actually feel that. Dolphins use this type of echolocation sonar. That's what sonar is in water. So water, the speed is about four times as fast in water, and as it is in air. And in wood, it's pretty fast as well. There's not a lot of things, I guess, in wood that you would like be able to understand what I'm talking about because you don't usually hear through wood. Iron, you do sometimes. Like so, for instance, if you put your head up on a railroad track like they did in the old movies, right? You can hear the train much farther off, much sooner because iron it travels so much better. I mean, look at this. This is just basically 1,000, and this is 5,000. So it's traveling. Sorry, not 5,000. It's 16,000, almost 17,000. So it's traveling almost 16, 17 times better through iron as it does through air. So what controls the speed of sound is the medium. So what means is that the more elastic and springy and close together the molecules are in the medium, the faster sound gets traveling um, through that substance. And the medium, once again, is the substance that sound is traveling through. This is actually pretty cool. You can sing into a glass and you can break it. So this guy is going to talk about this guy Jamie that basically just sings into these cups, and if he uses the right tone, boop, he can actually cause the cup to break. And so what he's going to do, so you can watch that video if you want to, but what he's going to do is in a high speed camera, and with the high speed camera, he's gonna play a tone. So when he plays the right tune, you can see the straws bouncing back and forth like crazy. But it's kind of hard to see what's actually going on unless you kind of like get a high speed camera and kind of zoom in. So he's going to show you exactly what's going on. So why does it break the cup? So now he's going to slow it down. super high def camera, and you can see it's doing this wiggling, right? And that's a really good one because you can see the standing wave. So as the sound waves come, they hit it perfectly at the right tone for that glass. And so if you hit the right tone for that glass, it's called its natural frequency, and it makes this really good you can't really see it. There it goes. This really good wave. It's a standing wave in the glass itself. So everything has a natural frequency. Like for instance, if I hit this, that's going to give you a tone, right? And that tone is the tone of this object, right? And so it has a natural frequency. If I was to sing at that tone, whatever that tone is, I could get this thing to vibrate strongly. And that's really what this natural frequency is talking about. If you do that enough, right? If you do that enough, the glass is going to break. I am. Pretty cool. So this is really an important concept in a lot of ways. And You really need to watch this video. This video is really pretty mesmerizing. One of those satisfying visuals when you're talking about waveforms. So, anyways, I'm going to pause this video and I'm going to come back in a moment.